Man, this problem is one chore. This is 377 combination sum 4. Given an array of distinct integers nums and a target integer target, return the number of possible combinations that add up to target. The test cases are generated such that the answer can fit into a 32-bit integer. We're going to code our solution in Python, so the fact that it fits or doesn't fit in a 32-bit integer, we don't concern ourselves with those trivial lower level language problems. Everything fits in anything. Every data type is any data type. We're chilling. So in this example, we're using nums equals 1, 2, 3. If it's not completely clear what I'm doing right now, I am referencing this example here. Whoa. And then we have target equals 4. So in order to reach target equals 4, we could use 1 plus 1 plus 1 plus 1, or 1 plus 1 plus 2, or 1 plus 2 plus 1, or 1 plus 3, or 2 plus 1 plus 1, or 2 plus 2, or 3 plus 1. And that means the total number of ways is 1, 2, 3, 4, 5, 6, 7. Now notice something interesting here, right, is that it's about the permutation, not the combination, because these are different, right? Like 3 and 1 is different than 1 and 3. So even though this is saying total combinations, right, we're actually looking for kind of like permutations. But if none of what I'm saying right now makes any sense, just ignore it. I'm just kind of diving into a discrete math statistics background. But just note that, 1 and 3 is unique from 3 and 1, right? 1, 1, and 2 is unique from 2, 1, and 1, and 1, 2, and 1, even though they're using the same number of each numbers, right? There's 2 1s and there's 1, 2 in each of these examples, but since you use 2 in the first position versus the second position versus the third position gives you a different solution. So one thing that's interesting about this problem, first, there's really 2 observations that this problem statement gives you. First one is you notice kind of the weird way in which the order is given, right? It's like we start with all ones, and then all ones, and then 2s, and 3s, and then 1s, then 2s, then 2, 1. So it's kind of like, this is kind of sorted in order somehow. It's like you process all the 1s before you process all the 2s, you process all the 3s, process all the 1s and the 2s and the 3s, 1s. So there's this like sorted order to this, right? Like 1, 1, 1, 1 is less than 1, 1, 2, which is less than 1, 2, 1 if you're talking about kind of the sorted order, not the fact, 1,111 is greater than 112, but you'll notice like this is the same, but this is greater, so it comes before that. It comes after that, right? This is the same, but this is greater, so it comes before the previous one. So there's this natural order, right? There's this natural increase of the digits in each place. So that implies something about how you solve this problem. In the second observation, which is key to solving this, I guess, not efficiently, but, sufficiently, is that, num's length is less than equal to 200, so it's really short, right? The array that we're dealing with is really small, and so is target. Target is less than 1,000. So, this is less than 10 to the 2, and this is less than 10 to the 3. So what that indicates to me is that it's okay if the solution is not time efficient or space efficient or whatever, right? Because I think one of the traps you can fall into if you're given this kind of problem is thinking there's some really efficient way of solving it, right? Thinking there's got to be some magical, recurrence relationship using dynamic programming and things connect. Oh, maybe there's a traversal. Oh, maybe there's, there's something, there's a prefix. What am I missing here that I can apply to make this problem optimal? But it kind of turns out that there really isn't. Maybe there is, but there really doesn't seem to be a solution that's that great. And that's okay. So maybe the best approach that you can do is just brute forcing. Okay? And what do I mean by brute forcing? Well, it kind of seems like the brute force solution here is to be like, well, I'm going to try everything I can using 1 and see what I can get remaining. And I'll try everything I can get with 2 and see what I can get remaining. And I'll try everything I can get with 3 and see what's remaining. So really what this problem comes down to is like, okay, I have some target value, right? And then I'm going to see, well, how many ways can I get to target if I remove some number in nums from target, right? So if I take a branch, what I'm basically saying is like, this is target minus nums at 0. And that's a branch. And then I have choices from there. And then I have an email. No, I'm joking. That's, if you work in corporate world, you know that's a very, very scary sound. And then I have target minus nums 1, right? And that's another universe. And da-da-da, da-da-da, da-da-da for all the target numbers. And then from this state, I can go target minus num 0 again. And build out the state like this, and so on and so forth. Now, if this is too general, let's just look at this example. So if we have nums equals 1, 2, 3 and target equals 4, well, I start with 4. And then what can I do? Well, I can use 1. So we'll create that link. I can use 2, or I can use 3. So what I mean by that is I can branch out into the situations where I use a 1, where I use a 2, where I use a 3, and I can build out this tree that represents using those numbers. So if I use a 1, now what is my target going to be, right? Because I need to create the target sum using nums, right? So I need a sum of some number of these nums to get to target, right? Like I could do a 1, a 1, and a 1, and 1, but it has to equal the target, right? So if I use a 1, right? If I use a 1, what does that mean here? Well, that means now that my target I have to get to is 3. Okay? And what else can I use? Well, I can use 2. Well, that means then that my sum is now 2. Or I can use a 3. Right? And when I'm saying use a 2, I'm just saying what numbers and what num and nums can I use to create a sum of 4? Well, if I use a 1, and I'm trying to sum to 4, that means now I'm trying to sum to 3, right? Because I've already used the 1. So it's like I've removed a 1 from my total target sum. And last but not least, I can use a 3. And if I use a 3, then what's remaining is 1. What about at this 3 state? Well, I can use any number of nums, right? I can use 1 4 times. So if I'm at 3, I can do the same thing. I can use a 1, right? I can use a 1. I can use a 2, or I can use a 3. Here I could use a 1, I could use a 2, I could use a 3, I could use a 1, I could use a 2, I could use a 3. So I started to branch out pretty quickly, right? Because every single time you add 1 to, you go to the next level of the tree, right? If I was to turn this clockwise or whatever, if I turn this 90 degrees clockwise, right? You could see this is obviously a tree structure. And let's just go through that. So if I could use a 1 here. I could use a 2. I could use a 3. From now on, I'm just going to put the number so I don't have to keep writing use. So I could use a 1. I could use a 2. I could use a 3. I could use a 1. I could use a 2. I could use a 3. Okay. If I use a 1 at 3, then I'm given 2. If I use a 2 and I have 3 left, I have 1. If I use a 3 and I have a 3, I have 0. If I have a 2 and use a 1, I got 1, 0, -1, 0, -1, -2. That's some quick counting. And people say that calculators are important. Calculators are useless, trivial tools used by barbarians. Just kidding. I don't even know how to count. Really. So let's just look at all of these. So far, given what we have, what can we state? Well, if it gets to negative, right, that means it's not a solution. Right, because we're trying to get to our target of 4, and this is basically saying if you use a 2 and then use a 3, you're going to overshoot by 1. You're going to get to -5. So that's not going to be one of the target sums. So if you get a negative number, you already know, okay, this is shot. Right, like I tried to use some combination of these nums and I overshot, I overreached, I overestimated, I overcounted, and I got past the solution, right? So if I use a 2 and then I use a 3, I'm not going to get 4. I'm going to get 5. So I went over by 1. So that's what this is basically accounting for. So all these negatives are no good. If you get a 0, well, that tells you a great thing, right? If you get a 0, that's saying that you found a combination of numbers that when used together, it gets you to the destination. And in this example, right, it's using 3 and using 1. Right, so that's one of the solutions. So this green path gives you a +1 to your solution. And look, that's the 3, 1 right here. Voila. So you can say the same thing about this solution, right? There's a solution where you use 2 and then 2. Oh, wouldn't you look at that? There's that solution right here. There's a solution where you can use 3 and then 1, right? Now, since this is like a permutation scheme, that's another solution, right? 3 and 1, and using a 1 and then a 3, sorry, right? So 1 and 3 are different than 3 and 1. That's why you can use a solution in your solution. Use a solution in your solution. I'm being very repetitive today. I'm repeating the same thing in a very redundant fashion. Okay, so we've already gotten 3 of the 7 solutions here. Now, what I'm going to do first is I'm just going to do this one. Now, one thing you should notice about the 1, why do I keep doing that? I keep being so redundant. For 1, what can you do for 1? Well, for 1, you can do 1, 2, or 3. But doesn't this 1 with a 1, 2, and 3 look mighty familiar? Doesn't this 1 with the options of 1, 2, or 3, right? I'm going to draw this blue. Doesn't this look identical to this? Right? This is the same subtree, right? The solution for this 1, we already found the solution if you have a target sum of 1 remaining. We already know what that is. So in a general case, what you could say is like, I don't need to think about the answer for 1 anymore. I don't need to calculate it, right? Because I already know what it is, right? The answer for 1, I've already done that. I already know that when you use a 1, you get 1 target sum here of size 0, right? I already know what the answer to this system is. Now I'm going to erase the blue and the green and all that. Oh, I'll keep the green. You gotta keep the green. Right, I already know what the solution is here for 1. Right, so I don't need to recalculate this. I can just reuse information. So that's where we're gonna use memoization, right? Because I already know this branch. Now this is a small branch. You're like, okay, you save 3 computations, good luck. But imagine the system was huge, right? And imagine a huge chunk of the system I've already calculated. So instead of recalculating it, it looks like in some cases I've already pre-calculated something I'm looking for. So if I just save that information, it'll save me a lot of heartache, a lot of headache. So I've already calculated that path. So now I get this additional one here and I don't have to calculate it. And guess what? Let's look here for 2. Well, I've already found 2. I found the whole tree associated with 2. So I don't need to recalculate this whole tree. Yet again, what can I do? What am I supposed to do when I'm all something and you're okay? What am I supposed to say? I've already found what this is. Boom. So I just saved myself even more computations, right? Because I've already calculated what 2 is. So I don't need to calculate it again. I just pull it from a previous thing that I've calculated. And now if I count up the number of zeros that I have, that results from counting a path. Notice I've exhausted everything else, right? I either got to 0, I got something to negative, so I went somewhere where I found nothing. I overshot, or I got to a solution. So how many solutions do I have? I have 1, 2, 3, 4, 5, 6. I forgot something somewhere. 1, 2, 3, 4, 5, 6. Why did I get 6, guys? What did I do wrong here? Well, let's see what solutions I got. So I got 1, 3. So doing some debugging here. So I can just follow these paths, right, to know what the trees are that I got. I got 1, 1, 2. I got 1, 1, 1, 1. 1, 1, 1, 1. 1, 3, 1, 2, 2, 1, 1, 1, 1. Okay. Oh, because I forgot this last path here, right? There's still a 1 here. So this one, again, is the same situation as this one. So I can just copy that over, right? So, sorry. Just a confusing game here. So I forgot to finish, right? Because you can't just have a 1 remaining. Either you end at 0 or you end at something negative, right? But if you have a 1 branch, if something's a 1 and it's a leaf, it can't be a leaf, right? Because if you have 1, that means there's still you're under the target. So you need to keep removing things until you get to the target. So that means there's another thing here. Now it's going to get sloppy. But that gives you the 7th one, right? 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6, 7. See, I told you I couldn't count. And that's all your 7 solutions. So if you just traverse down this path, you'll get there. But I'm not going to bore you too much with that. So with that, let's just go ahead and write the solution. Okay. So first thing I'm going to do is make sure that my trash is empty because my computer's almost out of storage. And yep, that would have been really bad because I would have lost this recording. And that's happened once or twice. And some of my best videos have actually been made. And you know, when you have a Mac, it just says, oh, there's no space. Not saving the video. It's gone forever. Goodbye. Right? Instead of just keeping it in RAM and telling you need to delete something. No concern. Nope, doesn't care. Okay, so how do we make this work? Well, we'll just call it T. I don't know, the function where we have a target. Okay, we'll just say, I don't know what to call it. We'll just call it T. We'll just call it DFS. So that way the interviewer knows that we're like super good with data structures. And we'll have self.m, which is going to be where we're going to keep information about the number of solutions that get you somewhere, right? Because after we solve something, we should keep the number of solutions that you get, right? Because in this example, we don't actually need the tree itself. We just need the number of values that you can get, right? The number of solutions you can get for any target. Right, so for 2, we would just say that there's 2 solutions that you could get. That way, when you get to this 2, you would just return 2. Okay, so this is more of a model of what's happening, but not actually the computation. Like, it's a model of the computations that you're doing, but there's so much extra information that's in here that we don't need. We don't really need to know what the combination ways are. We just need the number that exists. So when we're done with 2, we can just say, okay, from 2, we get 2 solutions. We don't need to keep what those actual solutions are or which solutions failed or whatever. Okay, so first thing happens is, well, if target is less than 0, right, that means you got somewhere, right? You got to some point where you overestimated or you overcounted. You went past the target and there's no going back. And since there's no going back, you got to close this crap. Why did I open that? That was a mistake. Don't be a fake. Okay, so if you go over and you're in the negative territory, you don't want to account for that. So you just say, okay, that's not a solution. So if target is less than 0, you say return 0. Sorry, it's not a solution. If target is 0, right? Now, actually, we're going to do this a little bit better. We're going to set this to be 0. And we're going to say, if we've seen target in self.m or target is less than 0, we return self.m at target. So that'll account for a lot of things. We'll just say self.m of 0 equals 1, right? Because if you get to 0, there's one solution there, right? There's one solution for 0, which is itself, which is just 0. So that's kind of like your base case in this recursive stack, right? So less than or equal to 0. Versus if target is less than 0, then it'll default by returning 0, right? So this is basically saying if we've already seen the solution, right here, right? If we've already seen the solution, like we've already accounted for the solution of 2. Remember, we counted for the solution of 2, and then we countered 2 again. So if we've already accounted for the 2 solution, then just return that 2 solution. So that's what we're saying here. So if we've already accounted for that 2 solution, then just return that 2 solution. Or if the target is less than or equal to 0. Well, this is basically saying, well, if the target is 0, then self.m of target is 0, which will return 1. But if the target is less than 0, then we don't have a solution here, and it will return something that isn't populated, and it will just return 0. Okay, so now we only need one of those. And otherwise, well, then what's the value of m at this target? Well, we want to save that information, right? We want to save the information for 2 so that any other subsequent call uses that information. So we say self.m of target equals what? Well, we're going to sum the number of solutions for all our children. So what are the possible things you get for any target? For any target, you can use the first num, the second num, the third num, and using that will take you to a state that's that num less than the original target, right? If I use 1, I go from 4 to 3. If I use 2, the new target is 2. If I use 3, the new target is 1 because I'm subtracting 3 from 4. It's 2 because I'm subtracting 2 from 4. It's 3 because I'm subtracting 1 from 4, right? So I'm at a state target. So then it's going to be the sum of what I can get from using the target minus the num for each num in nums, right? So I'm going to look at each num in nums. So it's going to branch out for each num in nums, right? In this example, the nums are 1, 2, 3. So I'm going to use the first num, I'll use the second num, I'll use the third num, and that'll take me to a new target, which is that num less than the initial target, right? So I'll use each num in nums, so 1, 2, and 3, and then I'll be at a state where I'm that num less than, right, the original target, which is just taking the target minus num and going to that state. And then when you're done with that, you'll just return self.m of target. And then we want to return this solution, and we're going to run DFS on the target. And there you go. What a wonderful problem this is. But, you know, this problem is like, this solution is more or less intuitive, right? Because you're literally just brute forcing your way through the world. But it's also kind of aggravating because you might be inclined to think that there's some beautiful dynamic programming, deep approach that allows you to somehow leverage things you've already done to quickly compute it. But that's not the world we live in. So if you're in an interview, always try to get information about the what do they call it? Just the size of your variables. I know the constraints, right? So try to get information about the constraints because that will reveal the nature of the problem. But again, like I've said in previous videos, that doesn't always necessarily mean that they're going to give you information that has any sort of implication, right? Maybe they'll just say there are no constraints. Or maybe they'll say, oh, num's length can be less than 10 to the 8. Even though there's no way that this solution could efficiently solve something 10 to the 8, right? If num's length was 10 to the 8 and target was 10 to the 8 or something, like this would take forever. It wouldn't be feasible, at least on Leetcode, right? So what's my point? My point is ask about constraints, and hopefully if they give you small constraints, then you'll know that an inefficient solution is workable. But also understand that if you ask about constraints, they can be intentionally misleading. So do with that information what you will. Okay, guys, have a good day.